Okay, so today we're starting chapter 6. And I don't think I've got any videos, so I didn't really need to load that up. Okay. So chapter 6, we're talking about Cassidy behind her back. No. We're talking about mechanical properties. We talked in chapter 5 about deformation, and in chapter 4 about deformation, and chapter 5 how those defects are created. But now in chapter 6 we're backing off to more of a macroscopic characterization of the materials and how they perform mechanically.
Can you talk about the deformation of legs, muscles, what were you saying?
So we're going to look at this from two standpoints. The first is tensile. We're talking about tensile deformation.
Like the trees that get Christmas.
No, that would be tinsel, not tensile. So we're going to define two characteristics, the stress and the strain. The stress is the force per unit area, kind of like pressure. Because if I pull on a thin metal wire, it's going to take a different amount of force to deform it than if I pull on a thick metal rod. Right, so I have to account for that somewhere because it's the same metal. So it is force divided by area. So in the context of this picture, area is the cross-sectional area, and force is the force that's used to pull. Okay? On the horizontal axis, we have strain, which is defined as the change in length divided by the initial length. Actually, that's not true. That's the engineering strain. Let me first define the real strain. So the real strain is the integral from L naught to L of dl over L. Okay, so as it elongates, each little piece elongates a dl. What?
I don't know, some stuff going on.
Just a little trouble focusing today?
Monday. Was up late last night.
Well, you said you went to bed early this morning.
Shh. So in other words, this little bit will have a certain dl over L, this little bit will have a certain dl. So we're going to integrate that along the entire length of the sample. Okay? And if we do that, when L naught is the initial length. If we do that, we get a curve that looks something like this. And I'm going to exaggerate it a bit. Okay, so what would really happen is this linear section here at the front would be really close to the axis to the point where you wouldn't be able to see it on the scale. So I've kind of broadened it out. So in this first linear section, there's a slope that we call E, the elastic modulus. So it behaves very much like a spring or rubber band here in the front end. I apply a load and I get a stretch, but it's a linear relationship between the load and the stretch. I apply twice as much load, I get twice as much stretch. Okay? Then there's a point up here, which we call the yield point. Where it begins to permanently deform. At any point up to the yield point, if I let go of it, it comes back down on itself. It follows the line back down. There's nothing permanent about the deformation. It stretches, but then I let go and it comes back.
Is that always true?
That's how, well, that's the yield point, that's what we define as the yield point. The yield point is the point where I start to do something to it that I don't recover when I unload it.
So if you use say a spring a lot,
Right.
over and over and
That's-
over,
that's-
never going past
Yeah,
it,
that's fatigue, that's a different
that's
phenomenon. Yes.
Is that supposed to be linear all the way up to the yield point, or it's supposed to be linear and then it kind of curves out?
It
and
might,
then
it might curve out a little bit.
Okay, so the yield point isn't necessarily in the straight section.
Well, when we talk, we mostly will use engineering stress and strain, which is a different diagram we'll draw in a second. And then I'll be more particular about how I define the yield point. Okay. Okay. So if I load it up, let's say I load it up to this point up here, and then unload it, so I pull it, I stretch it, I've deformed it, and I let it go, it will still relax along that slope,
which is the same slope.
which is the same slope. Right. So at this point, when it's loaded up to that point, there are several pieces of deformation, several pieces of strain. This piece is still elastic strain. It's called elastic because it comes back, right? Like an elastic waistband in your shorts or whatever. Right? So it comes back out, that's elastic deformation. Hey, we don't need to see the elastic waistband on your shorts. I'm just glad you didn't reach over and decide you needed to give Jesse a wedgie or something to demonstrate the elasticity of the shorts. All right? Elastic. Everybody understand elastic because it comes back. There's actually a little bit in here of what's called anelastic. That is, when it releases, it comes back to here, and then if you let it sit, it'll recover some of that. Okay, so if anybody's ever maybe stretched a piece of silicone or something, and then let go, and it comes back, and then it kind of shrinks back a little bit more. You know what I'm talking about? Okay, so that's the anelastic piece. And then the part that you're permanently stuck with is plastic deformation. So we have plastic, anelastic, and elastic. And the slope, as I indicated, the slope here is again the same modulus as the elastic portion.
Is the plastic supposed to be from under the yield point over?
Nope, the plastic is just some portion. It's just these three pieces.
Okay.
Anelastic typically in most materials is very small.
Why is it past the yield point though? Why is the
Because
plastic-
as I go past here, I'm still stretching it elastically. Right, so I'm still stretching bonds and stuff, but I'm also deforming it.
Okay.
So the yield point, if I stop it right here, just past the yield point, it'll come back to a very little, tiny little bit of plastic. Because it's how far I am beyond the yield point that is the plastic section.
So what makes the right boundary of elastic special?
The what?
The rightmost boundary of elastic special, because I could just go up further.
Right, that's just where I have to stop it before I let it go.
So really it's the left to anywhere beyond.
It's the release point. So if I took it up to just before this point and brought it back, right, that difference
Is that what the breaking point is?
would be the elastic. The elastic is just how much is relaxed when I let go of the load.
So the elastic regime is beyond the leftmost region, but doesn't necessarily have the rightmost limit.
Yeah, for a particular material, the elastic portion of the strain is the portion that is recoverable when I let go of the load. If I stretch it further, there will be more of that. It's always going to be E times the load, right? Or times the, yeah. In that linear region, that's the slope, right? Because the 0 is 0. 0 load, there's 0 deformation. So it's a proportional region. So if I want to find the elastic portion, bigger this is, the bigger the elastic portion. So the elastic portion will be the stress divided by the modulus. E is called Young's modulus. Or sometimes just called the elastic modulus. So that behaves according to Hooke's law. Remember Hooke's law from springs, right? Kx. Behaves according to Hooke's law in here, and anytime it relaxes, this part is the deformation. Yes?
You have like a big X like at the end of your.
Oh yeah, sorry.
Is that the breaking point?
So that's the point where it breaks.
Okay, cool.
Yeah.
Can you explain the inelastic part? Does it come all the way down and then go back even farther to the inelastic part?
So it comes back all the way down to here, and then as it sits, it recovers some portion.
Just kind of shrinks while it's sitting there?
Just it shrinks while it's sitting there, right? That's what I'm saying. If you've ever done this with some kind of,
Silly putty?
silly putty, yeah, so it'll happen with silly putty. Silly putty's a little wonky. Because I hate using silly putty in this context because it's just not.
It's just too silly.
It was kind of built to
It's
just
not,
be
yeah,
weird.
it's weird. So, but if you, as I said earlier, if you pull in a piece of silicone, stretch out a piece of silicone rubber, soft silicone rubber, and then let go, it'll come back. But then if you just let it sit there, it'll come back a little further. Right? So that's sort of the anelastic. That's kind of like what the anelastic would be. Okay.
What do you do with like the thermal, like, cause I mean, like when there's heat in something, it expands more. when you
Again, I
stretch
don't want to
something.
get into the that level of detail at this point because I want to make sure we get through all the other stuff. If you remember when I talked about plotting, now I'm plotting force here, not energy, versus A. Okay. Remember when I'm talking about there was a thing that did something like this. Right, because energy, then we had to take the derivative or integral or whatever it was. Right? So at this point, the zero force point is where the sort of rest state of this thing. So the slope along this line, right, the tangency there, that gives me my E. That isn't E because the units are not the right units.
What's A?
The atomic spacing. Right? But E is derived from the slope at that point. Okay, from the slope where A equals A naught, the sort of rest state of the material. Okay, a couple of things. So the yield point is there. There's actually sometimes defined a separate proportional limit. So back to Colin's question, I think it was Colin, that about is there a little bit of bend after that? There's a proportional limit, which is the end of the linear region, that may be different from the yield point. They're very close to each other, they may be coincidental, but there is a separate definition of the proportional limit. So you can get some non-proportionality right before it begins to deform. Okay, so you may see separate definitions of those 2 points. Okay, there's a couple other definitions we need. Poisson's ratio.
Poseidon's ratio. They should have used a psi instead of an E for that. Because then it would be like Poseidon's ratio. You know, because it looks like a triangle.
Moving on, Poisson's ratio. I'm sorry. And well, and I didn't. It's not defined with an E, so I don't know why I wrote an E in the first place. It's actually a new.
It should be something.
Poisson's ratio is defined as minus the strain in the, that's what I do, X divided by the strain in the Z direction for and a stress applied in the Z direction.
Is that
Yes.
you said?
I'm sorry, I'm going to address the person who has his hand in the air. Yes, sir.
Is that a newer gamma?
That's a new. It's a new.
Brand new. Is that Poisson?
Poisson.
Yes.
Is that better? Okay.
Doesn't that mean fish in French?
You know,
You okay?
it's Monday, you're not really supposed to be silly like this on Monday.
You okay, DL?
Be ready to jump on to work.
Calm down.
So,
I don't give
Poisson's
you-
ratio, what does that mean? EX over EY, well what that means is, or EX over EC, what that means is, if this is my coordinate system, in which case Y would be out the back, and I pull it in the Z direction, it's going to shrink in this direction as it elongates. Right? So again, if you want to use silly putty as an example, if I pull on a tube, if I make a little snake out of silly putty, right? Roll it together in my hands, make a snake, and then I pull on that snake, what happens? The snake gets skinnier, right? It shrinks. There's lateral contraction as I elongate the sample. So there is a strain, a delta L, in the X direction as I pull in the Y direction and elongate in the Y direction. So Poisson's ratio is the ratio of those two. Okay. And in this case, it would be equal to minus EY over EZ. Right? If I'm pulling in the Z direction, the strain in the lateral direction, it doesn't know the difference between this direction and that direction, assuming it's a homogeneous isotropic material. Okay, like silicon. Okay, so the yield point is there. The convention for defining, because it's really hard to define if there's some nonlinear elasticity here, it's really hard to define the point where it actually begins to become permanent deformation. Right, I mean, you have to load it up and then let it go and remeasure. And load it up to a slightly higher load and then unload to remeasure and so on. You have to just keep going up and down the curve until you finally get to the point where, okay, it's a micron longer than it was before, I've had permanent deformation. Okay. So what we instead typically use for the yield point is the point at which the plastic strain is equal to 0.2%. In other words, where it deviates from the elastic region, when this linear region slides over by 0.2%. The horizontal scale is a percentage typically.
Why is the plastic region the region on the left and the elastic the region on the right?
Because when I let it go, the elastic region comes back, the plastic doesn't. The plastic is stuck.
I thought it was stuck when it's, I thought it restores when it's on the left end there.
No, I mean, think about it. I stretch it, it's this long now. Right, it's undergone 50%, it's 50% longer. I let go of it, it comes back, now it's 30% longer. Which means there was 20% elastic that was recovered, and 30% plastic that's left.
So plastic is basically whatever it is once you let it go.
Right, plastic is what's there when you let it go.
Okay, because I was thinking you're kind of just labeling the regions on the line where
No, it's
in
the
the
amount.
beginning.
It's the amount.
So each of those
Value.
regions only refers to
This is
one
a-
point you would pull.
Right, this is a particular value. Right, the length of that section is the plastic and elastic amount. Okay? Does that make sense for science? Okay. Okay, so one of the other things that you can kind of see from this then is if I take it up to this point and then let it come back, and then I load it up again a second time, it's going to have to get up to here before it starts to deform again. So by deforming it and then letting it go, I've actually increased the yield point. You see where I'm? I've made it harder to deform the material. And we call that strain hardening. So, for example, if I have a coat hanger, metal coat hanger, I know that's sort of foreign anymore, right? Everybody uses plastic now. If I have a metal coat hanger and a nice straight piece of wire, and I bend it over the edge of this table. Okay, let's make it steel wire so it's fairly stiff stuff. So I bend the steel wire over the edge of the table, right? Then I go to bend it back. Can I ever get it to bend back at the same point? Right? You can't, right? I bend one piece of wire, I got to bend. I want to straighten it back out again. I'm always going to straighten it out at the section next to it. And so I take my wire and it's bent like this. I unbend it and it's going to unbend right from that, right? So I'm always going to be left with some kind of a wiggle in my wire.
I hate
Right.
that so much.
The reason for that is, once I've deformed it, I've made this stronger. It takes more load to bend this section now, to deform this section, than it does the sections around it. So when I apply a load to straighten it out, that load is going to, the material adjacent to the bend is going to yield before the section in the bend.
So what forging is?
That's what that happens in forging, but that's not what forging is. This strain hardening can happen in forging, but in forging generally you work at a high temperature. A lot of stuff we're going to talk about. Okay. So you see what I'm saying though? That section, once I've bent it, becomes harder, and so it's darn near impossible for me to bend it back because all the stuff around it is softer and easier to bend. So when I apply a load to bend it back, I'm going to bend it in that softer region before I bend it in the harder region. That is strain hardening. And that's actually typically measured, this hardness is usually measured by the resistance to penetration. So in other words, if I want to characterize a piece of material that I have hardened, I would measure it by putting a known indenter, like a known little ball, a hard steel ball, on it with a fixed load and see how big of a dent it makes. The harder it is, the smaller the dent. So you measure the hardness by measuring the indentation. Okay. All right. So all of this is sort of good, what I would call true stress and strain, or what is called true stress and strain. However, it's going to be really hard with a real material to do an integral of some measured quantity, right? That's going to be kind of impossible. So instead of true stress and strain, we generally work with engineering stress and strain. So here we define engineering stress as force divided by the initial cross-sectional area. You see why that would be different than this? Why would that be different? Why would I want to differentiate area versus the initial area?
Your area will change.
Right. As I pull on it, it shrinks. Area gets smaller. Right. And I don't know what that is unless I'm measuring it constantly and constantly doing that calculation. And engineering strain is the change in length over the initial length. So you can kind of see how they have the same kind of approach. But here we're calculating a single value for the whole thing instead of trying to integrate along the length. Yes?
So we're going to use those definitions all that often then?
So in terms of, yeah, you need to know the definitions.
Yeah.
So sort of a theoretical analysis. But in reality, in a practical sense, when you're actually working with a piece of steel or something, you're going to use engineering stress and strain.
So for the class, we don't need those though, but like
For the real world, we probably primarily use those. Okay. And as a result, we actually get a slightly different behavior here. Still linear in this section. Up to the yield point. But now the curve bends over. essentially what happens is there becomes some point out here where the cross-sectional area is reduced so much that the stress that was increasing over here, because it was divided by that smaller number, right, now decreases here because we're still dividing by the larger initial value. But this is actually very useful, because what that means is this point right here, which we call the UTS, the ultimate tensile strength, is the maximum load, represents the point where the maximum load that you can ever support with this wire or whatever it is we're pulling on. Because all we're doing is taking force and dividing it by a constant. So the maximum force occurs at that point. That ultimate tensile strength would be somewhere in the middle of this graph. We wouldn't be able to just look at the graph and know that's the maximum load this can support. But over here, we know right away. Okay, and again, I've exaggerated this. This sloped region should be very close to the axis, and this whole thing just stretched out quite a bit. So I've exaggerated the thing just to show you the points. And then the braking stress would be right there. So that's the stress at the point where it breaks. And if I extrapolate the braking stress backwards at a slope of E, what I'm left with is the PEF, the percent elongation at failure.
Does failure in this case mean an absolute snap?
It means an absolute snap. It means it breaks, yes.
So why do you extrapolate it back instead of just going straight down?
Because when it breaks, each piece will then release the elastic strain that's in it.
Okay, then you just measure those two atoms together and you say, hey look, this is the length.
Right.
Right, so that point though, if we're saying it's a percent,
Yep.
it's not really, that's a stress, that's not, but that's a strain, it's not a percent.
Right, but the strain can be listed, it's a unitless quantity. It's length over length. So it can be listed as a percent. What percent of L naught is delta L? And typically, this horizontal axis is given in percents. That's the units, if you will, of the horizontal axis.
Did you say UTS is the ultimate tensile strength?
Ultimate tensile strength. Right. As much as, so failure, percent elongation of failure, it's defining failure as coming apart. In many cases, failure may be yield. Right? If my steel beam bends, then it has failed. In many cases, right? If the steel beam supporting this floor, well, it's probably mostly concrete, there's steel underneath it, but if the steel beam supporting the roof of Odal suddenly are bent, they fail. Right? So failure is different depending on what your context is, but it's still sort of ultimate failure.
So breaking strain and percent.
Breaking strength and percent elongation at failure. Percent elongation at failure.
How do you differentiate between the bending and just a regular, shoot, what I'm looking for? Just the regular, deformation of the, deflection of the beam? Like, how do you differentiate?
So it's deflection, so deflection of a beam is, in theory, not permanent, right? So deflection of the beam resulting from a load, if I step off the beam comes back,
Yeah.
right? If it bends, then that means the beam is permanently deformed. I step off, it comes back a little ways, but it's not straight anymore.
Okay, so you're just talking about after the yield point in this context?
Right, so here
Okay.
it's
I
back.
thought you were saying over the whole thing, but yeah, I got it.
Okay, any other questions about that? Okay. So let's see if we can, so if we have true strain, is an integral from L naught to L of dl over L, well, we can actually analyze that integral, right? That becomes the natural log of L over L naught, right? Which is the natural log of L plus delta L over L naught. which is equal to the natural log of 1 plus the engineering strain. So the engineering strain and the true strain are correlated. We can measure the engineering strain, just measure the elongation at any point in time, measure the initial length, and then through a natural log, get at the actual true strain. So we can use this curve using that information. Yes.
Probably should be one thing I'm not seeing, but why can you replace L with L plus delta L?
L naught plus delta, sorry.
Okay.
Right, that's how I got the 1. Because that was the 1. Okay. So, and the same thing could then be true in the horizontal direction. If I put a micrometer on here and measure the horizontal EX, right, I can get the epsilon X. If I measure the EY, get the epsilon Y. Right, so if I can get epsilon X and epsilon Y, nu, or for that matter, if I just measure EZ this way, and I know what Poisson's ratio is for that material. Each material has its own Poisson ratio, just like each material has its own Young's modulus. Right, it's a material property. If I know Poisson's ratio for that material, then I can find EX. If I know EX, I can find A, so I can get the stress. So I can get from engineering properties to true stress and strain properties using this relationship. Okay. So we can do true stress and strain, it's just that, so you asked earlier, so I can forget this basically, you use this in class and then use that. In the field, when you're measuring, you're going to measure stuff here. But this is still accessible to you.
Yeah, yeah.
Okay. Let's see here. Now, I've used S and E here, and sigma and epsilon. Unfortunately, people don't hold to that convention rigorously like they should. Okay, that is the true convention. S and E are engineering, and sigma and epsilon are true. But you'll find people using S or sigma and epsilon for engineering stress and strain. Okay, so don't rely on the fact that sigma is different than S. Because somebody will use, find somebody using sigma instead of S, but meaning engineering strain. The other thing is, we measure this. If I have a sample, a piece of wire, actually let me use that one for the time being. If I have this piece of wire, and it breaks right there, I don't necessarily know that the entire wire has gone all the way through this curve. Maybe only this little section here went all the way through the curve. Right, and experienced plastic deformation and everything. So it's a little tricky to assume that the entire thing is behaving uniformly. So what we usually do is we usually create a dog bone specimen. It's supposed to be symmetrical. Anyway, like this. So we grab hold of the end here with some kind of a fixture that clamps down on it, and the end here with some fixture that clamps down on it, and pull on it. And then we know that from here to here, in this part where it's nice and cylindrical, that is our gauge length. That's where all the action's happening. And that way we don't have to worry about the fact that when I clamp down on something, I'm adding extra stress to it. Right? Because usually I'm clamping down with something that's going to tear into the metal. Something that's got sharp teeth on it to hold on to it, if it's a metal sample. Well, when I tear onto the metal, I'm going to create like little cracks and crevices in the surface of the metal. And so I want to make sure that those ends where I'm grabbing onto it are much bigger, have a much larger area, and therefore experience a much smaller stress. So that all of the real failure here occurs in the central region. Yeah?
Is surface integrity
really important for like.
Yeah, we'll talk more about cracks. We'll talk about cracks. Surface defect. Okay, in fact, I threw that in here, yeah. All right, so, I'll mention it briefly here then, in just a second. So, one of the things that's also of interest, that's sort of not necessarily captured here, is the area under this curve. So if we just draw kind of a straight line there. The area under the curve, if you think about it, what is this, what is the area under the curve in terms of what we actually have in these two numbers?
Integral of SDE.
Right, it's the integral of SDE, so what would the integral of SDE be?
It sort of measures the stress over the whole thing, the whole length.
Is it what?
Work.
It's work. If you think about what this is, that's the integral of force per unit area times dE, which is going to be dL over L naught. Right? Which is equal to the integral of F dL times 1 over the volume. So the area in that curve is the work per unit volume, or the energy absorbed by the material per unit volume in the process of deforming it. And we call that toughness. For kind of obvious reasons, right? If something's tough, it can take a lot of energy. You know, it can absorb a lot of energy. Glass has a very high yield point. It is very difficult to get glass to yield. But glass on this curve, right, has a very high modulus of elasticity too. So glass would look like this. Right? Because glass doesn't deform much. It just breaks when it gets to the top. So the toughness of glass, right? What do I want to do here? Fairly small. Rubber, on the other hand, rubber band, right, stretch forever. So let me do that. Rubber band stretches like man, goes forever, right? But it doesn't ever hold much load. So rubber band, again, smaller toughness. So you want to compromise those two. So steel is tough.
Because like it takes a while, like
It takes a fair amount of yield, strength to yield it. And again, remember I've compressed this graph, so this is actually very wide. Steel will stretch quite a bit before it breaks. Okay. Again, energy per unit volume. The thing that actually makes glass not very tough is the fact that in glass, let me just do this in blue. The maximum stress, we'll talk more about this later, but since Colin brought it up, the maximum stress is on the order of 2 times the applied stress times the square root of C over rho. Because where C and rho are, C is the length of the crack, and rho is the crack tip radius. So what happens is in a piece of glass or a piece of brittle material, you can form cracks that will magnify the stress in the material. So that even though glass takes a tremendous amount of stress to break, if there's a little bit of a defect on the surface of a piece of glass, just a little nick, something, that little nick will cause a much larger stress to be present at the point where the nick is occurring. And because the glass is brittle, it won't deform much before it'll propagate that crack across. So what happens in most cases with a glass material or ceramic or any kind of brittle material is that it's in fact the surface preparation that determines the strength way more than the material properties. If I polish a glass surface really smooth, I get it really smooth, I can get it 10 times as strong as if I polish it only pretty smooth. So the surface preparation is entirely the thing that matters.
Just in tension, right? Not, I mean, it's not.
Just in tension, right? Or in bending, because in bending you get tension on the top and compression on the bottom. Right? Anytime there's tension, right? So a glass window, right? If I want to go punch my hand through the glass window, if that glass window was really strong and was really nice and perfect, I could punch on it all day. It actually probably wouldn't break. Right? But if there's just a little bit of a ding, I punch it, the whole thing shatters. Okay? All right. Let's see. So that's all tensile deformation, and I've got 4 minutes to cover shear. Holy moly! All right. Let's see if I can at least get you the basic picture for shear deformation. So the equations in shear are very much the same as they are in tension. Okay, and I'm just going to go ahead and draw the back corners solid. Because now I'm going to shear it. I'm going to apply a load, a force in that direction. I'm pushing kind of like the deck of cards. Slide the top over the bottom. So what ends up happening is I get that kind of deformation. Everybody see how that would happen? So here I've applied a shear force to an area here. So before, when I was applying a tensile load, right, if I applied a tensile load in the horizontal direction, it would be the area of the end face. It was the cross-sectional area perpendicular to the force. It was the area perpendicular to the force that determined the stress. Here, it's the area parallel to the force. Or more accurately, the area of the surface who is that is defined by the cross product, that is defined by the intersection of the force and the moment created by that force. So the force is here, the moment is in this plane, so those two form that area. So now I have a shear stress, tau, that's equal to the shear force divided by that area naught, and shear strain gamma, that's equal to dx over z naught. As opposed to delta L over L naught. So now the dx is still in the direction of motion, or in the direction of force, but now z is perpendicular to that direction. And those two will, in the linear region, be related by a constant which we call the shear modulus. Or sometimes called the modulus of rigidity, if that comes up in any of your homework problems. But it turns out that for, again, homogeneous isotopic materials, there's a relationship between these. E, Young's modulus, is equal to 2 times the shear modulus times 1 plus Poisson's ratio. We're not going to drive those relationships in here, I'm just giving it to you. So in other words, you don't have something different in the shear direction than you have in the tensile direction. They're correlated. The behavior is measured differently, and so we have this different kind of behavior, or this different, the functional, the analytical behavior is different because of the way we measure it. But it's still based on the same principles, Young's modulus and Poisson's ratio. And for what it's worth, in bulk, that's in shear. In bulk, that is, if I submit something to hydrostatic loading, I drop something at the bottom of the ocean, so it's being squeezed equally on all sides. In bulk, the pressure, the hydrostatic pressure, is equal to a constant K, which is the bulk modulus, times delta V over V. So now instead of delta L over L, we use delta V over V, because it's squeezing equally in all directions, so we just use the volume, the change in volume. And again, this is the bulk modulus. And P is pressure, hydrostatic pressure, but again, it's in units of force per unit area, same as this. And just as I said before, everything's defined by 2 terms, E over 3 times 1 minus 2 nu. So that's related to the other things as well. There's a couple other characteristics that your book lists. A modulus of rupture, which is used when you can't pull something in tension. If I want to check the tensile properties of a brick, right? I can't load it in my tensile machine and pull on it. That's not really going to do it. So there's a modulus of rupture test where basically support it on 2 points and push down in the middle and see how it breaks there. And then there's a flexural modulus that results from that. But I'll refer you to the book to read those things. You guys say any questions? But yeah. So, I don't know what the process is. So if you were giving a presentation, not giving a presentation, I don't know how they do that. Speaking of which, did you talk to your construction for that? For you go to the conference.
I should be able to make that.